Thank you everybody, and thank you Juan for introducing me. I'm very happy to be here to be here virtually to give this talk. And I do want to emphasize that I do want to encourage a lot of questions. So if you have any questions at any time, please speak up. So today I'm going to talk about a set of surprisingly large corrections to the page curve near what is known as holographic entanglement transitions. And this is based on a paper that I wrote recently with Huajia Wang, and also it's related to a paper that was written by Don Meroff, Shannon Wang, and Zhenchen Wang that appeared on the same day. So, and I'm using this spotlight, the red dots on the screen to highlight any area that I want to point to. So let me know if you cannot see the red dot. So the plan today is to, first I'll describe what is a phase transition in a holographic entanglement entropy. And I'll present what are these enhanced corrections when we're right at a phase transition. To give some intuitive argument for why these enhanced corrections exist, I will give an intuitive explanation using gravitational saddle points. And in the process of doing that, it will be clear that it is easiest to do this argument using fixed area states. So we will also introduce that. And to make everything very concrete, I will also present a tractable example of black hole microstates where we can actually do the calculation honestly and find the corrections. And finally, I will end with some discussions. So that's the plan. So, and by the way, if at any time you cannot see my full screen, if there's an area that you cannot see on my screen, just let me know. Sometimes the screens are showing up differently on everybody's screen. So let's first start by talking about the Van Neumann entropy of a subsystem in quantum gravity. So this is the main topic of the talk. This entropy has a few different names. Sometimes people call it entanglement entropy. Sometimes people call it the quantum entropy. Sometimes people call it the fine-grained entropy. For me, they're all the same, and I will call it the Van Neumann entropy of a subsystem. And it has been a very important topic recently, especially having played a central role in understanding the black hole information problem. So in ADS-CFT, we often choose the subsystem to be a boundary subregion, A, and the entropy will then be given by what is known as the Rotak-Yanagi formula. So I've written down the Rotak-Yanagi formula here. And the important term is the first term on the right of the formula, which is the area of an RT surface, in general, an extremal surface that is anchored at the boundary of the region A. And in this talk, we will not need the quantum correction, which is the second term on the right of this equation, which corresponds to quantum entropy in the bulk coming from the entanglement wedge, little a, in the bulk. So for this talk, we will focus on the leading term, which is of order 1/g. The interesting cases are when there are two or more competing RT surfaces. So I've drawn schematically two possible examples of this kind. In the first example, you can say that there are two possible surfaces because there's some gravitational curvature, there's some curvature in the center of the space, maybe because of a massive star or maybe a pure state black hole. That results in two possible extremal surfaces that goes from either from the left of the massive star or to the right of the massive star. You can also take an example where we have a disjoint region which which consists of a top piece and the bottom piece in this picture. And there are two competing RT surfaces because there is a disconnected topology and a connected topology. So they compete. According to the Ruta-Yanagi formula, what we should do when we have two competing RT surfaces is to choose the one with a smaller area. So we would simply look at the area of the first RT surface gamma A1 and then the area of the second RT surface gamma A2, and then choose the minimal one. And this will result in a page curve for the entropy versus the subregion size. So as subregion size A grows, entropy first grow, but eventually needs to come down. And for a pure state that we're considering, the entropy needs to reach 0 when the subsystem reaches the full system. So the first phase, the increasing phase, is associated to one of the RT surfaces, and the decreasing phase is associated to the other RT surface. And there's a phase transition on the top. The phase transition, which strictly is only a phase transition if we take the small g limit, it happens when the two competing surfaces have equal area. So that should be fairly obvious from this equation. So that's the phase transition. And now, near the phase transition, it turns out that there is a surprisingly large correction to the page curve. I don't know if everyone can see, because I'm not really good at making such a plot, so I simply hand draw. I drawn by hand a very thin red curve underneath the previous K page curve. And the claim is that that is the actual entropy as a function of the subregion size. And the largest correction comes from very close to the region of the plot, very close to the phase transition. And the size of this correction, let's call that delta S, which is the difference between the sharp curve and the more smooth curve. This correction delta S is goes like of order 1 over square root of G. So it is much larger than what we might have expected from quantum corrections. The quantum corrections to RT comes from the bulk entanglement wedge, and that's only order 1 or order G to the 0th power in the small g limit. And this term, this correction is enhanced in the sense that it is much larger than that. So just to give a concrete example where this happens, we can consider an energy eigenstate for the full system. And for various reasons, it's simplest if we take some kind of thermodynamic limit where the volume of this whole system goes to infinity while keeping the energy density finite, or keep it large. It doesn't matter as long as it doesn't go to 0. In this case, the correction is very simple if we calculate it at the transition point. The transition point is precisely 1/2 when the subsystem is 1/2 of the full system, and at that point, which is the peak of the page curve, the correction goes like minus the square root of C over 2 pi, where C is the heat capacity. So in a holographic system, the heat capacity goes like 1 over G, and therefore this correction goes like 1 over square root of G. This is a result that was previously found in chaotic many-body systems without using holography in 2 papers, first by Vidmar Regal, and the second recent paper by Murthy Renyí. So eventually I will use this as a tractable example. Yes.
Is this not really just the usual? I mean, in large entropy systems, but finite, there are entropy fluctuations that believe are exactly this size. Is that what the origin of this effect?
I think it is precisely the origin of effect, and we're right now seeing it in holography. And in particular, for example, yes, you mentioned entropy fluctuation. In this context, it either presents as area fluctuation in holography, or in this energy eigenstate situation corresponds to subsystem energy fluctuation. So the answer is yes. And we will see that more clearly when I talk about how to see this in holography.
Thank you.
Sure. So the plan is that I will actually use this as a tractable example to show that this can also happen holographically, because holographic theories are chaotic. But I want to also use this example to understand the origins of these corrections in more general holographic systems, so not restricted to this example. But before saying more about how to understand these corrections, let me point out two features of this correction. The first feature is that this delta S decreases exponentially if we go away from the transition point. So if we ask how large is the width of this exponential decrease, it is set by when the area difference between the two competing RT surfaces becomes of order square root of G. So it's a fairly small region. And if we go a little bit far, if we go order 1 far away from the transition point, we're not going to see this correction. This correction will be exponentially small by then. So this is why we call it an enhanced correction at a transition. The second feature is that we may also consider the Renyí entropy as a generalization of the von Neumann entropy. And the Renyí entropy is defined in this way, in equation 4. The statement, we can ask whether enhanced corrections also appear in the Renyí entropies. The answer is that it only appears very, very close to n equals 1. So for Renyí entropy with n equals 1 plus epsilon, and for sufficiently small epsilon, it will be there. But if we go to reasonably large n minus 1, it will disappear. The precise statement is that it will decrease exponentially, just like the function e to the minus n minus 1 squared over g. So once n minus 1 is much larger than the square root of g, this correction has been exponentially suppressed. So it would be very hard to see these corrections in, say, for example, the second Renyí entropy or higher Renyí entropy, because it would already be exponentially suppressed by then. This is something that backs an explanation in terms of subdominant saddle points in a gravitational path interval. When we compute, for example, the second Renyí entropy or higher Renyí entropy using gravitational path intervals. So we'll come to that, we'll return to that in a moment. I'd like to give, before presenting details of a tractable example where we can derive this, I'd like to present some intuitive explanation, which is perhaps not completely precise at this stage, but it will be confirmed by the example that we're going to do later. So what we're saying is that there is a large correction that was previously not known to the RT formula as we know it. The RT formula was derived by the replica method using a method by Locois and Marcena. So what we should really do is to revisit that to find where we can find the loophole where enhanced corrections could appear. So we will start then by considering the Renyí entropy, or simply trace rho to the n for integer n. And the standard story is that this is determined by a partition function on the replicated boundary, and then by using ADS-CFT calculated by a replicated gravitational path interval. In particular, for every integer n, we need to calculate this gravitational path integral by summing over contributions of all bulk saddle points obeying the replicated boundary condition. So let me schematically write that as saying that what we want to calculate, trace rho to the n, is equal to sum over all the saddles, where the contribution of each saddle is, roughly speaking, e to the minus I being the action. Here, I'm suppressing fluctuations around the saddle points. We can include them. They're not going to give large corrections. They're going to give order 1 terms, and not something that goes like 1 over square root of g. The standard story then that follows is that we will then keep only the most dominant saddle and discard the rest, because we can, by doing that, we can easily analytically continue to non-integer n and eventually take the n goes to 1 limit and find the Ryu-Takayanagi formula. If we did that, we will find the Ryu-Takayanagi formula with a prescription that is always given by the area of the smaller surface. And there will be a sharp transition with no enhanced correction. So what we're saying then is that this must be wrong. Somehow the subdominant saddle points, even though they are very small, they conspire to contribute something like e to the minus n minus 1 squared over g with some prefactor. And if you had something like this, then it's very tricky, because this contribution is exponentially suppressed at all integer n greater than or equal to 2. So if we compute the Renyí entropy, it would be very hard to see this. You have to be very careful. But when you analytically continue to n equals 1, this term is no longer suppressed, and it makes a non-negligible contribution to the von Neumann entropy. And in fact, with the prefactor that I have here, it will make a contribution at order 1 over g, 1 over the square root of g. So this is the kind of thing that we have to look out for. And it turns out that in the tractable examples that we will discuss, this can be verified. The subdominant saddle points indeed contribute something like this to make the enhanced corrections appear. So we need to do an honest calculation. We need to sum over all saddle points, not just including the dominant saddle, but also include all the subdominant saddle points, and then analytically continue the sum in a very careful way. And this is very difficult in general, because in particular, in this sum over the saddle points, we need to include both replica symmetric and replica non-symmetric saddles. So just to be very explicit, we can write it as a sum of 2 replica symmetric saddle points labeled by RS, and a number of replica non-symmetric saddles, R and S. And in particular, the replica symmetric saddles are easier to understand. They can be thought of as the n-fold cover of the original bulk manifold branched over either the first RT surface or the second RT surface. So it simply essentially extend the replica method on the boundary to the bulk, either by using the first RT surface or the second one. At least topologically, that's what it is, and then we can solve the equation of motion to find the saddle. the non-replica symmetric, the replica non-symmetric saddles are much more complicated because they can branch over different RT surfaces. They're branch covers, but they branch over different RT surfaces on different copies. So for example, if we consider the n equals 3 case, which is the third Renyí entropy, then we in principle needs to include a replica non-symmetric saddle constructed in the following way. So this is supposed to be a bulk prescription for constructing the saddle, at least topologically. We take 3 copies of the original bulk. There are 2 possible RT surfaces, let's call them A1, A2. And then we're going to cut open each one of the 3 copies in the red and the green regions. So we're going to open a slit on the red and green region, and we're going to glue the 2 red regions together cyclically. That means once we have opened the slit on the first red region and also the second one, the top of the slit on the first red region is glued to the bottom of the slit of the second red region and vice versa. And we do the same for the green region. You can check that this is a saddle, this is a topology that satisfies the replicated boundary condition. But it doesn't respect the bulk replica symmetry, the Z3 replica symmetry in the bulk. So it's a replica non-symmetric saddle. There are many more of these in general, and the number of these saddles, which is called Cn here, varies with n. So this is something that makes the analytic continuation in n very difficult. You cannot hope to analytically continue each one of these saddles, and you have to first do the sum and somehow analytically continue the sum.
She had a question.
Yeah.
What's the argument that it has to be branched across the original A1 and A2s?
This is just a description of the topology, and then we solve the equation of motion and smooth out the conical excess.
Is it guaranteed that after you solve the equations of motion, the A1 and A2 are going to be the same ones as in the replica symmetric saddles?
They're not going to be the same ones in the sense that each saddle will look different, and the replica non-symmetric saddles, for example, will have different areas. So A1, A2 here just labels, maybe I should call them gamma A1 and gamma A2. They're not going, the area is not going to be the same. They're settled down to some different area in the replica non-symmetric saddle compared to the replica symmetric saddle. Is that your question?
Yeah, that was my question.
Okay, I'm sorry for the misunderstanding. Yes, the A1, A2 here should really just, you should think of them as gamma A1, gamma A2. They are just surfaces.
If you don't introduce, I think Ahmed's point, if you don't introduce these fixed area states, then in general, the back reaction can be more complicated than you're saying.
Exactly, yes. Right now I haven't introduced the fixed area state.
Okay, but a family of saddles such as you suggested probably doesn't necessarily exist, except in the fixed area world. There's, in other words, there's no general way to construct them, so there's no general reason to think they really exist.
So at least in cases where A1, the 2 surfaces are topologically inequivalent, the gluing construction that I have here gives a topology that is distinct from for example, from the replica symmetric topologies.
Yes.
And I believe that we should be able to solve the equation of motion in that topology.
Maybe. Okay.
I don't have, so we will see that in particular in the example, in the tractable example that I'm going to discuss, that is clear. I don't have a mathematically precise argument for why this should be true, but I feel like within the topology, I should be able to find the solution. Maybe that's wrong, and maybe I'm mistaken, but this is the assumption I'm going to work under.
Just to understand this point a little better, the manifold you just described has some singularities at the surfaces.
Exactly, and that's why I said this is only going to be the correct topology. And once we have fixed this topology, we're going to solve the equation of motion, and that will smooth out the conical excesses on the surfaces.
So you're defining this in such a way that when we go through both surfaces, you have a CN cyclic permutation, right?
Yes, exactly.
And
so
then you're splitting, you have different
exactly.
permutations.
Exactly. There is a permutation group around A1, or the first RT surface. There's a permutation group element around the second RT surface. The composition of those two gives the boundary cyclic permutation.
Okay.
Yeah.
Is there a constraint on the permutations beyond that one, or?
I think anytime we can create something like this where an element, we can essentially split the cyclic permutation of the boundary into the composition of two permutations, and then we can implement the two permutations on the two surfaces. I think in general, if we can do this, that defines a possible topology in the bulk. And I'm going to think that we can find a solution within that topology. Now, maybe they're not dominant. We'll come to that in a moment, but we, in principle, should somehow.
Okay.
Yeah. So in general, I hope I have convinced you that this is a formidable task in general, summing over these saddles and analytically continuing. But in very particular examples, this nonetheless can be carried out. And we will see one such example later, an example of black hole microstates. I should mention that there is actually another example that was also carried out in similar fashion, which is discussed in the appendix of the West Coast Replica wormhole paper. And there, a similar square root of 1 over G correction is found that smoothes out the phase transition. So this is a different example that I'm going to present. So before I present the details of the example, I'd like to describe some intuitive argument for the enhanced correction. Of course, this kind of explanation was motivated by the lessons we extract from the example, but it's good to see the story first before we go into too much technical details. So the story is the following. We should rewrite, at least the best way to see this correction is to rewrite the gravitational path integral by postponing until the very end the integrals over the areas A1 and A2. So right now, okay, from now on, A1, A2 means the area of the two surfaces. In a gravitational path integral, we in principle need to integrate over all degrees of freedom of the metric and possibly other fields, but we're going to leave the integrals over A1, A2 until the very end. And we can do the rest of the path integral first. The rest of the path integral is then calculated in the so-called fixed area states. And in particular, we can write down the path integral in a way that leaves the integrals over A1, A2 undone. And having done the rest, we simply sum over what is known as the fixed area saddles. So these fixed area saddles depend on the choice of A1, A2, and they satisfy the equation of motion away from the two surfaces. Because we have fixed the area of the two surfaces, we don't expect the equation of motion to hold on those two surfaces. But away from the surfaces, the equation of motion holds, and that's why we call these saddles with the fixed area constraint. So I want to give some background for the fixed area states in case people are not familiar. And if you need more information, just ask me about more about the fixed area state. So the way I think about the fixed area state is that we can start in, for example, ADS CFT, we can start with a general semi-classical state that is prepared by a gravitational path interval. We can call that state psi. And then we can project it to a state by restricting the path interval to only integrating over metric configurations that satisfies a constraint. And the constraint says that the RT surface gamma A needs to have the desired area A. So we can label this fixed area state by the number A, and the general semi-classical state is then a superposition of the fixed area states. The nice thing about
sorry, Shi.
Yes.
When you say, so if I give some geometry, this you're calculating the extremal surface in that geometry.
Yes.
And then after you calculated the extremal surface, you're fixing its area. Is that the procedure?
Yes. One needs to be slightly careful when the metric configurations that we're going to discuss possibly has conical defects, because these, in general, these fixed area states are dominated by geometries that have conical defects. So when we talk about the RT surface, we just need to remember that it could also be a surface that lies on a conical defect.
Shi?
Yes.
Here you're integrating over space-times where gamma A is extremal in all of these space-times. Is that the idea?
We're integrating over space-times in which it is extremal in all directions. Is that what you're asking? In both directions, in fact.
Yeah. Well,
because it's co-dimension too.
So the area of the surface is kept the same, but it seems like there's also a restriction on the space-time just outside the surface because you want it to be extremal. It just seems like that it's not just a boundary condition on the surface, but also derivatives away from the surface.
Yeah, perhaps you can say that. It's a restriction. What I'm going to say doesn't depend on whether it's just a restriction on the surface or a restriction also for some information about the metric slightly away from the surface. The important thing is that if you look at the metric configuration G, it is allowed when the extremal surface that you find in that G has the area A. So I guess what you're saying is right. Yes, this is the constraint, and that's the constraint we're going to impose.
Okay, thank you.
Sure. So the nice thing about these fixed area states is that they have a flat entanglement spectra, because if you compute their Renyí entropies, the Renyí entropy is n independent up to and including the one loop order, so all the way to g to the 0th power. And roughly speaking, this is because you have fixed the areas, you have fixed the entropy, even the Renyí entropy. And as I mentioned, the general state is then a superposition of fixed area state. And we know that the general state in holography in ADS-CFT has non-trivial Renyí entropies that depends on n. And that n dependence is solely because of fluctuations of the area. And just as a side comment, we will see that the enhanced corrections that we're going to talk about today are also, in some sense, entirely due to area fluctuations. And this is in agreement with Tom's comment earlier that is related to entropy fluctuations.
Sorry, I have also
Yes.
a question regarding the definition. So as far as I understood, it's like a reorganization of the gravitational path integral,
Yes,
where we just integrate over A at the end. But
yes.
so the configuration for the metric that might enter might be crazy off shell, far away from ADS. And are we
Good.
guaranteed that extremo surface will exist in that geometry? Because then we will be dropping those configurations from this integral. Like if just that area does not
Yeah.
exist in that.
That's a very good question. It is an issue that comes up because in off-shell configurations, we're not guaranteed to have an extremal surface. And all I could say is I don't have a completely clean procedure for dealing with those very off-shell configurations. It doesn't affect what I'm going to talk about today, because this is really a trick of reorganizing the sum over the saddle points. And therefore, if we discarded part of the parameter space, the configuration space, which are very off-shell, then it doesn't really affect the leading order contribution to the path integral. So I think if we really need to understand the path integrals very precisely, if we want, I think it's something that we probably need to sort out if we want to understand this, for example, non-perturbatively well in G, then we need to sort out how to deal with those configurations. But right now, we don't need to do that.
Okay,
Does that convince
was very
you?
helpful. Yes,
Okay.
thank you. That was very helpful.
Okay, good. Okay, so let's come back to our problem. We have two competing surfaces, RT surfaces, so it's natural to consider a slightly more generalized fixed area state where we have both areas fixed, A1, A2. The saddles are then, the fixed area saddles are then to be summed, that we're going to sum over are simply solutions with the fixed area constraint that sets both areas to fixed values. Now, the important point, this is probably the most important and surprising point of the talk. The important point is that once we're inside the integrals over A1, A2, because we're working with fixed area states, we can discard the subdominant saddles. These are subdominant fixed area saddles. And we can only keep the dominant fixed area saddle. So in other words, we can rewrite this sum over fixed area saddles, which includes many crazy saddles, which are non-replica non-symmetric, into just a dominant contribution, taking the maximal value among all the saddles, plus an order 1 contribution that will not affect our enhanced corrections. So we can safely drop those. In other words, the total contribution is bounded by the total contribution of all the subdominant fixed area saddles together is bounded by some order 1 bound and doesn't lead to any enhanced corrections at all. And this is true, and in particular, we need this to be true not just for integer n starting with n equals 2 and so on, but we also want it to be true when it is analytically continued to n equals 1. And this is why it's not easy to check this, but it is true, as we will see in the example we're going to discuss. I want to point out this is exactly the opposite of what we said before when we didn't work in the fixed area basis. Before we worked with the fixed area states, we said it is important to keep all the saddles, including the subdominant one, because if we didn't, we won't find the corrections. Here we're saying the opposite, but there's no contradiction. The fixed area states does its magic. And they're really important helpers in getting the story right. And once we have done this, the integral over A1, A2 will tell us everything. So just a note, you might find this difficult to believe, given that I especially said we shouldn't do this before in the beginning, when we're not considering fixed area states. So you might find it difficult to believe that it makes such a difference to work in a fixed area basis. I will show it in a, it is really equivalent to the diagonal approximation conjectured in the paper by Maroff and Wan. And also, it is easy to see this in a tractable example. So let's continue by keeping only by assuming this is right and keep only the keeping only the dominant fixed area saddle. This is then easy because it's one of the two replica symmetric saddles. Due to the fixed area states, due to the fixed area constraints, they are not only topologically given by the n-fold cover in the bulk, but also geometrically. In other words, because we're fixed both areas, we no longer need to include non-trivial back reaction. We simply replicate in the bulk and create a conical excess, and that's okay. The on-shell actions then of these two replica symmetric saddles, one of which will be dominant, are simply given by replicating the original saddle. So the I of A1, A2 is the action of the original fixed area saddle, n equals 1. We replicate it n times. And now we need to add in these area terms that corresponds to, roughly speaking, the conical excess. So each one of them will contribute n-1 times the corresponding area over 4G, and we have two possible values for the area. Of course,
so
then
here you have a CN singularity in each area.
No, only one. There are two replica symmetric saddle. The first one.
Sorry, you're talking still about the replica symmetric. So sorry, thank you.
Yeah. This is the replica symmetric case.
Okay, thank you.
Yeah, because as usual, the dominant saddle should be replica symmetric. At least that's what we believe. Yeah. So we can easily find the dominant contribution by figuring out whether A1 or A2 is smaller. And therefore, we can plug this. This is the on-shell action for the dominant saddle, where if we take the minimum over A1, A2, we find the on-shell action of the dominant saddle. And then we can plug this into our previous formula for the trace row to the n. And after some trivial steps, we can take the analytic continuation n goes to 1 because everything is explicit. We will find that the von Neumann entropy is given by this expression. And here we are doing still the integral over A1, A2. We're taking the minimum of A1, A2 divided by 4G. And it's going to be weighted by e to the minus the action of the original fixed area saddle, and Z1 is simply the normalization factor. So roughly speaking, this means that we're going to take the average weighted by e to the minus I of the entropy in each one of these fixed areas states, because the minimum of A1, A2 over 4G is the entropy for each fixed area state. And this is something that can be shown. This is the same as the diagonal approximation used in conjectured in the paper by Maroff, Wang. And I will say more about it later, but the important thing is that we can do this integral over A1, A2 explicitly. In the small g limit, it's dominated by the behavior of this function I near its minimum, so we can do a Taylor expansion, finding this Gaussian piece and changing variables to A plus and A minus. we can write the minimum of A1, A2 as A plus minus the absolute value of A minus. And I'm sorry for the typo, which I mean that we can then express the A minus integral, not the A2 integral, A minus integral in terms of an error function because of the absolute value. And the final result is simply the following. The leading term, of course, is the Rutakanagi formula, taking the minimum over A1, A2. The bar here just means the saddle point value in the full general semi-classical state. So that's the minimum of this action I. And then there is this correction piece coming from the error function, where phi is a function that is determined. This is using a notation that has been useful in previous papers. Phi is a function that is very sharply peaked around 1. Around x equals 0, and it has a height of 1. So the second term here is very sharply peaked around the phase transition because it goes like the argument has 1 over square root of g. And the magnitude of this correction is indeed 1 over square root of g. Here, sigma minus tilde is just something that is related to the variance of A minus in the distribution e to the minus 1. And in particular, we have defined the variance in a way to extract the prefactor g. So sigma tilde is of order 1. So we found the enhanced correction. Next we will basically justify our dropping, all the subdominant fixed area saddles by looking at a very tractable example, and because of that we can see the enhanced correction explicitly. Essentially, we're going to sum over all the saddles in the high energy limit and see the sum is actually not so different from the subdominant fixed area saddle.
A quick question, if you can go up.
Yeah, sure.
The equation 12, so that minus sign is important, correct?
The minus sign, do you mean this minus sign?
Yes. Yes.
Yeah, it is, I think it's important. Well, it should be a minus sign. Well, if you think how to make the page curve smooth, it should be lower than the page curve.
That's right. Okay, thanks.
Yeah. So what we're going to do is to consider in holographic CFT a microstate, a black hole microstate drawn from a typical state from the microcanonical ensemble around energy E. So we're going to write the state as E comma C hat, where C hat is random choices of coefficients for within some energy window of width 2 delta. If we consider such a state, this is a fairly random state. Its reduced density matrix on subregion A is simply tracing out this full density matrix, and it can be represented by a Euclidean path integral on a strip where we open a slit on A, and also the specification of the state C hat can be thought of as something that we put on at the 2 boundaries. And this is a little rough, but it will be clear what I mean when I compute the trace of the powers of density matrices. So we're interested in doing the average over all choices of C hat. We're not interested in a particular value, but we're interested in the average. This is implemented by contracting pairs of C hat boundaries. So for example, if we compute the average of row A, well, there are only two C hat boundaries, so we can contract them in pairs and join them. And this gives, roughly speaking, a cylinder. And in this picture, it looks like a cylinder. But if we really think of A and A bar in the floor system with no boundary, then this is like a torus. So this gives an emergent KMS condition with some effective inverse temperature beta for the microcanonical ensemble. So we actually need to compute not just rho A, but the trace of rho A to the nth power and then average. So when we do this, we make n copies of the strip. Here's a picture where n equals 3. We make n copies of the strip and then glue the slits along A cyclically and contract the n broad C hat boundaries with the n cat ones. So contracting the top with bottom. And there are many ways of doing this and factorial ways of contraction. So they all give different closed manifolds that we need to sum over. So in the equation, this means that we are summing over CFT partition functions on these different contracted manifolds. We will calculate this by summing over the corresponding bulk saddles, but we will see that the sum is actually dominated by only a subset of these guys. And the subset corresponds to what we can call planar or non-crossing contractions. Because of time constraint, I will just say this without proving it. We will from now on we will focus on these planar contractions, and in pictures when n equals 3, we have 5 of these. The first and the last are replica symmetric. The middle is not replica symmetric, and actually by permuting what we do, permuting the 3 copies, we can get 3 different manifolds. What we will do, we will have to construct bulk saddles with these boundary conditions. So it is very helpful to first rearrange these manifolds into a canonical representation where the C hat contractions happen within each individual strip. The cost of doing that is that the gluing on A and A bar will be very complicated. So for example, if we do n equals 3, then M1 is already canonical. M2, 3, 4, denoted by this middle picture on the top, will have to be arranged into the left panel of the bottom picture, like this, where the green lines denote how we glue A and A bar among the different copies. But the contraction for C hat is always within each strip. This is just a reorganization of the gluing procedure. It's topologically completely the same. For the M5, the second replicated replica symmetric manifold, we can also arrange it into a canonical representation. Now, if we have the canonical representation, then it's easy to construct a bulk saddle, at least topologically, by extending whatever we're doing on the boundary into the bulk. So, so again, for n equals 3, the 5 possible bulk topologies are now given by the corresponding gluing in the bulk. And to be very precise, what we do is that we use the gluing procedure on A, on the boundary, to glue the corresponding homology hypersurfaces, which we can call sigma A, which are orange in these pictures in the bulk, where the homology hypersurface, as usual, has a boundary which is A union gamma A. And gamma A is some kind of analog of the first competing RT surface. And for each cycle in the gluing for A, we have a distinct gamma A. So there really are a number of these gamma A surfaces, these quote unquote RT surfaces, where the number can be is the number of A cycles in the A gluing, which we denote by M. And the same statement holds for A bar. We glue the blue hypersurfaces, and the analog of the second RT surface can be thought of as gamma A bar, but there are a number of them. The number is actually fixed in this case to be m+1 minus m due to the planar contraction. The idea is then we're going to impose the equation of motion. This is generally difficult to solve, but if we take a high energy limit where all the RT surfaces are essentially hugging the black hole horizon, the black hole horizons are the dotted lines in the middle, then the edge effects can be ignored and things become very simple. Because in this limit, so I'm going a little fast because time is short, but these details can be worked out. So the point is that in this limit, the equation of motion simply reduces to n equations, and they are normal equations, non-differential equations, requiring the total ADM energy to be E on each copy. And this will uniquely fix the remaining n betas on each copy, remaining n parameters, one on each copy. And the feature of this solution is that all the A cycles, so all the A cycles have the same total beta, and all the A bar cycles have the same beta A bar, regardless of their cycle length, regardless they're glued to each other or glued to themselves. So what this means, if you think about it for a while, is that the saddle can actually be constructed by joining two kinds of pieces. The first kind of piece is a tube. We can call that BA, which is the bottom thing on the right here. This is a bulk tube corresponding to the region A, and we make M copies of these guys. And then the second piece is a similar tube, but for A bar, and we make m+1 minus m copies, and we're going to join them in this way to build the solution. Again, the edge effects are not important. We're hoping the edge will work out by themselves without affecting the on-shell action. So the story then becomes the following. All the RT surfaces for A have the same area, and all the RT surfaces corresponding to A bar have the same area. We can call that A1 and A2. This is because we only have two kinds of tubes. And then the saddle have the same on-shell action as the solution of a slightly different path integral, where in this path integral, we simply integrate over the action in this way. This can be thought of as a path integral in a ZN replica symmetric situation where we insert two kinds of conical defects along A1 and A2. And the way you convince yourself is by figuring out what the saddle point for equation 17 is, and convince yourself that it's actually a different version, a different gluing of the tubes that I mentioned earlier, where the first kind of tubes are glued together, creating a conical excess 2 pi m, and the second kinds of tubes are glued together along the RT surface with an opening angle of 2 pi m minus m plus 1. So it's just a different representation of the same thing with the same action. But the nice thing about 17 is that now you can sum over it. We can sum over all the saddles by computing the sum of this different patterns, the rewritten path integral, with a number n of n comma m, which is the Narayana number, which is the number of planar contractions with m acycles. The nice thing about this is that the sum over m can be done explicitly, and we arrive at the path integral with this kind of effective action, where the effective action is given in terms of an area term plus a log of a hypergeometric function, depending on whether A1 or A2 is smaller. This is something that is very natural to evaluate in a fixed area basis, because the total path integral can be done by first fixing A1, A2, and doing the rest of the path integral, giving something like this, where the saddle contribution for the fixed area state goes into the action I of A1, A2. And then we perform the final integrals over A1, A2. This is something that now can directly verify our previous claim that we can discard the subdominant fixed area saddles, because we can see it. The effective action comes from summing over all the fixed area saddles, but it only differs from the contribution of the dominant saddle by an order 1 number. So the dominant saddle is going to be the first term in this equation, the definition of I effective. The second term, which is the order 1 term, that is the log of this hypergeometric function. And because of the way that it is defined, the last argument is always between 0 and 1. And this term is always order 1. And this is true even when n is really close to 1. So this justifies our claim that we can just keep the dominant saddle point in the fixed area states, and we can find the enhanced correction following our calculations earlier.
Sorry, see, I got distracted. Where did the hypergeometric function come from?
It comes from this sum using the Lariana number that comes from, that essentially is the counting of the number of contractions with MA cycles. And it comes from rewriting also the saddle for each given value of m in terms of a slightly different path integral, but it really constructs the same thing using giving these tubes, but just in a different way where the tubes are glued together.
I see. So it's an analytic continuation of this sum of exponentials.
Yes, exactly. Okay. Because once you have done the sum, this is essentially a clever way of rewriting the thing that is not easy to analytically continue in a slightly different way that we can do the sum and analytically continue.
Okay, thank you.
Sure. So in this example, it cleverly does what is normally considered difficult. But we can show what we want then. So I'm out of time, but I just want to very quickly mention the diagonal approximation. Maybe in 1 minute, I'll mention that we saw this is the thing that is surprising, and we didn't have a good justification in it unless we are talking about a particular example. And this is the thing that is responsible for the correction. But the question is, why should this be true in general? And the idea is that if you write a general state as a superposition of a fixed area state, and then trace out a bar, you get this for the density matrix on A. But it has a diagonal and off-diagonal contribution. And if we make a diagonal approximation that says the off-diagonal contribution can be ignored when we compute the Van Nooyen entropy to the order that we need, then we can just keep the first diagonal term, and that will precisely give what we had in the beginning. So this is an equivalent way. This is really an equivalent way of our previous saying our previous conjecture that the subdominant fixed area saddles may be thrown away. The off-diagonal contributions here are very related to the subdominant saddle points that we threw away in that case. So in using a diagonal approximation, it is easy to arrive at what we wanted in the beginning. So let me end with a few quick questions. Yes.
Sorry, just a quick question about this part. Maybe this is too naive, but if you compare it to what you were saying before about why the saddle point approximation fails in the full Renyí problem, there's some interesting interplay, interesting dependence on n. Is the point that the fixed area states exactly eliminate that because they give you a flat entanglement spectrum, and so that's why this works? Is that the intuition?
It's not as simple. Let me agree with the first half of a sentence while wanting something more than the second half. I would say yes. The story is indeed that by using the fixed area states, we have essentially eliminated the subtlety that would lead to the enhanced corrections in the general state. In other words, the enhanced corrections only come from area fluctuations. Now, why in fixed area states we don't have this problem? That's very related to the diagonal approximation. I don't think it's as simple as saying that they have a flat entanglement spectrum and therefore we're done. One reason is that we're here considering a slightly different kind of fixed area state where we fix two areas, A1, A2, and one of them is out of the entanglement wedge. So this really goes into how to justify the diagonal approximation. And this is my first question here. How do we derive it from the gravitational path integral in general? And I also want to ask a few other questions before ending. How do we enjoy these corrections? They are very nice. They're kind of small, but larger than what we might expect from other corrections. How do we enjoy them? In particular, do they tell us anything about bulk reconstruction near phase transitions? That would be something interesting to know. And more generally, can we use these to understand more about quantum gravity on holographic states, perhaps showing that they must come from a very special type of quantum error correcting code, especially near a phase transition, and maybe using some kind of toy model like tensor networks to mimic these. So let me end here and thank you all for your attention. And I'm sorry for slightly running over the time, but I'm happy to take more questions.
Okay, thank you, Xin.
You're welcome.
Are there more questions?
Yeah, I have a question.
Sure.
Was it crucial? So this, it seemed to me, was crucial for you to do some averaging over this vector that you called C hat. Is that correct?
In this example, yes. I would like to say that the same statement is true even in standard ADS-CFT. For example, remember the two interval situation that I had in the beginning? That is simply a phase transition between a joined Archi surface and a disconnected Archi surface. And in that case, well, we can perhaps mumble some words about ADS-CFT intrinsically have some kind of random averaging, but the story shouldn't depend on that. And I would like to say that in ADS, this is a feature that we should be able to say, we should be able to derive just from gravitational path integrals. In my example, the averaging made everything easier, but I don't think that's necessary.
You expect if you consider an actual pure state, you would get the same answer?
I think we would be able to get very close to the same answer. Each individual energy eigenstate or each individual realization of the black hole microstate will certainly have small fluctuations from its average value, but I don't expect those deviations to be large. I expect this to be self-averaging.
Okay, thank you.
Sure.
I have a question. So in the beginning, you showed a formula from the general quantum systems, which had a precise coefficient multiplying the heat capacity.
Yes.
So my first question is that precise, the 2 pi, and do we reproduce it from gravity?
Yes, indeed. I didn't show it, but that's true.
Okay.
If you do the fixed area states, essentially, if you calculate, so I had a precise formula here. So this formula, equation 12. If you then plug this, if you then do this for the black hole microstate example, in a black hole microstate, there is a funny thing. The Gaussian distribution normally has a correlation matrix. Has this Gaussian coefficient matrix is generally is generic in general holographic situations, but in a black hole microstate where the total energy is fixed, it's highly correlated. So it actually is a one-dimensional trove, one-dimensional valley. So that makes the calculation easy, and if you carry it out in that example, you get precisely the heat capacity over 2 pi with a square root.
I see. Thank you.
Sure.
Hi, Shi. This is Douglas. I wanted to ask a question I've asked you before, so sorry, but I just wonder if you have a new perspective on it. Could you imagine some gravitational argument that there's a nice analytic continuation in N that has the properties we expect for a trace row to the N?
And I think you're asking the question in the with all the replica non-symmetric saddles included.
Yeah. Yeah, exactly. This is something that I roughly, did I mention this in the diagonal approximation discussion here? Not really. So, but let me answer a question. I mean, at least provide some my thoughts on it. My personal opinion is that it would probably be fairly difficult to try to write the full answer, including all the replica non-symmetric saddles into with analytically continued N into a gravitational path integral, because at least to me, analytically continuing these replica non-symmetric saddles are pretty complicated. And this is true even if we try to use fixed area states. And this is precisely related to the off-diagonal, sorry, to the fact that we don't yet have a gravitational way of arguing that the off-diagonal contributions here must be small. Because if we had a way of writing it out using path integrals, then we should be able to then analyze it and find that it is indeed small. So my thought is that while it is maybe not easy to write down a concrete path integral formula for the quantity that you asked away from integer n, there may be some kind of neat argument that gives a bound on the error we make when we replace, when we throw away the subdominant saddles, when we calculate the Van Neumann entropy. So in other words, even though we might not have a way of directly produce the analytic continuation of the replica non-symmetric saddles from path integrals, maybe we can bound them and say that they don't contribute to sufficiently leading orders in G near n equals 1. I think that's a perhaps more easier strategy
to understand their contributions. I would certainly love to have an expression for general n, but if we can understand its bound near n equals 1, that's already something that we can hope for.
Okay, thanks. That seems to already assume that makes sense to continue near n equals 1. Like, maybe
it assumes there is analytic continuation. It doesn't assume that the analytic continuation is given in a simple way by using any kind of path intervals. It's just a formal analytic continuation using Carson's theorem. But if you can still bound the analytic behavior of the analytic continuation and near n equals n, that's useful.
Okay, thank you.
Sure.
Okay, any other question? Well, if there are no more questions, let's thank Xi again for a very nice talk.
Thank you all for your attention.
Yeah, thank you very much.